This video lesson covers box diagrams and the 3 rules that are taken into account when filling box diagrams. Box diagrams are a convenient way for scientists to represent the energy levels, their orbitals, and their suborbitals. And typically what happens is we draw box diagrams starting from the bottom to the top. So let's begin down here. Closest to the nucleus is the first energy level, and it contains an s orbital. Now the first energy level is too small to have any other orbital types, and so there's just one orbital in the first energy level, the s. Now moving up to the next energy level, you'll see that the second energy level consists of 2 orbital types, both in green, the 2s and the 2p. But as we talked about in the last video lesson, the p orbital is actually broken up into 3 parts, and we represent that by a larger rectangle split up into 3 equivalent boxes. Now moving further from the nucleus, once we get to the end of the 2p, there are no more orbitals in the second energy level. So next starts the 3s. So the 3s followed by the 3p, and then as you can see up here in red, the 3d. Now we get a little bit of an overlap between the 4th energy level and the 3rd energy level. And this is an anomaly of the way that orbitals are organized around the nucleus. It would be nice if things just went S, SP, SPD, SPDF, but it's not that easy. In fact, there's some little bit of overlap. The way I describe it to some people is imagine the 3rd energy level represents this thick this thick green line. And the 4th energy level is going to be represented by this red line. Well, the thing is that the 4th energy level, it would be nice if the 4th energy level just sat on top of the 3rd energy level like that. But in fact, the 4th stretches down into the 3rd energy level, and so the 3rd energy level ends after the 4th energy level begins. Or in other words, the 4th energy level begins before the 3rd ends. So essentially, it's considered some overlap of energy levels. There's not a clear boundary between the 3rd and 4th energy level like there is between the 3rd and 2nd. As represented here, there's a clear boundary here between the 2p and 3s, but there's not a clear boundary between the end of the 3rd and the beginning of the 4th. So you might be asking yourself, how in the world am I supposed to know the order of which the orbitals exist? Because that's important moving forward. And here I'm going to show you a little something on how to help you figure that out. Start by making a column of all of the s orbitals, starting with 1s and down to 7s. Next, we're going to do the same with the p's, but the p's don't start until the 2nd energy level. So the first one will be 2p. So we've listed the column of p's from 2p down to 7p. Next, we're going to do the same with the d's, but the d's don't start showing up until the 3rd energy level. As you can see, now I have a column of d's starting at the 3rd energy level. And finally, we'll list a column of f's starting at the 4th energy level. So now you have this matrix, this columns and rows sort of situation. Next thing I'm going to do is I'm going to start drawing arrows diagonally starting at the top right and down to the left. Here's the first arrow. The next one is going to go on the line below it. As you can see, it goes through the 2s. Now the next one is going to go through the 2p and the 3s. And then starting over from the top, going down and diagonally to the left, 3p 4s, 3d 4p 5s, 4d 5p 6s, 4f 5d 6p 7s, 4f 6d 7p, finally 4f 7d, and finally 7f. So here's how this is read. If you take a look at the top left and start counting the arrows, basically listing the elements, starting from the top arrow, you start with a 1s. Then the arrow goes back to the start of the next arrow, which goes through the 2s. And then you double back to the beginning of the next arrow, which goes 2p, 3s. And then you double back and go back to the 3p, 4s. And that continues on and on and on until you have a continuous string of energy levels and orbitals. And as you can see, it continues on and on and on until you go through all of the energy levels and orbitals. This now lists all the energy levels starting with the 1s, followed by the 2s, then the 2p, 3s, 3p, 4s, 3d, 4p. And that is where you begin to see that overlap. After the 4p is over, it actually begins with the 5s, then the 4d, so you got some overlap between the 5 and the 4 and the 5. and then again in the 5 and the 6. And so there's some overlap going on all the way down. So in the next slide, we're going to talk about the 3 rules for filling these box diagrams. I've sketched out the orbitals and energy levels in order starting from the 1s up to the 3s. Now there are more orbital boxes after the 3s, but these are going to be the ones that we need to help us explain our 3 rules today. It's worth noting that these boxes and the order of the boxes never change. No matter what element you're talking about, they all have the same energy levels and orbitals over the top of their nucleus. The only difference between the different elements is that some elements have more electrons than others, so some need more boxes than others. But your first elements are simply going to fill the lowest energy levels available, which actually brings us to our first rule, the Aufbau principle, which says when filling boxes, electrons occupy the lowest energy level and orbital first. Basically what it means is if an electron has a choice, it's not going to hang out in the 3rd energy level, s orbital. No, it's not going to hang out up there. In fact, it's going to try and occupy the lowest energy level and orbital first. Now, for electrons, we represent them by either up arrows or down arrows. If there's 1 electron in a box, it's an up arrow, and if there's 2, it's an up coupled with a down. And so, for the first electron to go in, it has just 1 up arrow in the 1s. Now the next electron, say you have helium with 2 electrons, instead of having 1 up arrow in the 1s and 1 up arrow in the 2s, the Aufbau principle says you fill up the lowest available box, energy level and orbital first. And so, instead of having 1 in the 2s, we're going to put a paired up electron in the 1s. Now, can you put more than 2 electrons in a box? Well, we talked about this in the last video lesson, that only 2 electrons can fit into any particular orbital and suborbital, orbital if it's an s, suborbital if it's a multi-suborbital orbital, like 2p. But this brings us to our next rule, Pauli's exclusion principle. Pauli's exclusion principle states that there may be no more than 2 electrons per suborbital. And the second part of Pauli's exclusion principle states that those electrons, when paired, must have opposite spin. Now I put the word spin in quotation marks, meaning that they're not truly spinning, but we point them up and down as having opposite directions. Basically, if an electron is on one side of the orbital, the other electron, its pair, is in an opposite side so that they're never in the same spot at the same time. Now I'm going to scroll up here to give myself a little bit more room to write this 3rd and final rule. It is known as Hund's rule. And Hund's rule states that when filling electrons in an orbital with multiple suborbitals, the electrons fill 1 in each box before doubling up, which is the most stable way of filling an orbital. Mr. Ott likes to refer to this as the school bus rule. If you go on to a school bus and all the seats are empty, you sit in any one seat, but the next person on the school bus is going to choose a seat not in the same seat as you. Everybody will sit in their individual seat before any one seat gets 2 people. So pay close attention to the 2p box in the upper right hand corner here. So the first electron that goes into a 2p orbital will go in no problem. But the next one will go into an open seat, and the third then would go into a third yet open seat. Now only once all 3 boxes have 1 electron in it, the 4th electron can then choose to sit next to any other electron, thus doubling it up. It is inappropriate to fill electrons unevenly using Hund's rule. The first electron goes into the first box and the next one goes right next to it? No, that's weird. That doesn't happen on the bus. That doesn't happen with electrons. They tend to spread themselves out before doubling up. What you're looking at is a worksheet that I used to hand out to my kids, but now I've embedded it into the notes. As you can see down the left-hand side, we're looking at elements of increasing atomic number, and I also listed the element symbol. Now we're going to skip this section because that's part of a future video lesson. We're going to come over here. I've listed the order of the boxes in order from left to right. And this is where you're going to practice filling in the box diagrams for each individual element following the 3 rules that we just discussed. Now as you can see, the boxes are pretty tight. We can zoom in using notability magic, but oftentimes I like to use slashes and X's to represent electrons instead of arrows. So instead of up arrow, down arrow, as I have listed at the top, I put a slash for 1 electron and an X for 2. So let's start filling in the boxes starting with hydrogen. over here, hydrogen has 1 electron and it goes down into the 1s box. There you go. Now the next element is helium, and it has 2 electrons. The first one goes into the first box, the next one follows it right next to it in the 1s box. Now lithium has 3 electrons, so 1, 2, and then 3 goes into the 2p. And finally, beryllium has 4, 1, 2, 3, 4. Now we've gotten to the 2p orbital, which has actually 3 boxes, and so you can see across the top the 2p is bigger because it is made up of 3 parts. So boron's got 5 valence electrons, 1, 2, 3, 4, 5. But this is where Hund's rule comes into play, where we're going to put 1 in each of the 2p boxes before doubling up any. So carbon has 6, 5, 6, and nitrogen has 7, 1, 2, 3, 4, 5, 6, 7. You can start to see a pattern emerge that everything that you fill in is the same as what it was above it plus 1 more electron. And that should make sense to you because we're simply adding a proton every time we go down by the atomic number and thus adding an electron. So just take everything above and add 1 electron in addition to it. So oxygen, for example, has 8 electrons, and it's anything that nitrogen is plus 1 additional electron. And I'm going to double up the first 2p box. Fluorine then comes in and has 9 valence electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9. And finally, neon has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that fills up the second energy level. So the next one will be sodium with 1 electron in the 3s, and then magnesium with 2 electrons in the 3s. And then everything else before it will be filled. So in truth, you can identify an element if you only have seen the electrons and you know it's a neutral element. You can identify the element based on its box diagram because no 2 elements have the exact same box diagram, which is pretty cool. So once again, we've reached this point of aluminum where we're venturing into a p orbital. So when filling this set of boxes down here for aluminum, make sure that you put 1 in each before doubling up, just like you did in the 2p orbital. Aluminum has 1 in the 3p, silicon has 2 in the 3p, and phosphorus has 3 in the 3p, and sulfur will have 4 in the 3p, and since we have 1 in each, now we can put that 4th now, doubling up 1 of the 3p boxes. Keep in mind, don't get lazy here. You should fill in all of the boxes before the 3p to have a full box diagram. So there you have it. The application of the 3 rules. 1. Aufbau's principle says, fill lowest energy level in orbital first. Pauli's exclusion principle says, no more than 2 electrons per box and they must have opposite spins. And finally, Hund's rule applies only to p, d, and f orbitals, or those orbitals with multiple boxes that say electrons will fill evenly 1 in each before doubling up. That takes care of this video lesson. Thanks for listening.